an update for the Resource Prospector mission. We actually started this week with a little review of where we are in the Resource Prospector mission on Sunday, and it's quite an exciting mission that I think this audience is going to love to hear about. So, Dan, thanks.
Good morning, everybody. I was here last year introducing the Resource Prospector mission, and a lot has taken place. I went back and reviewed where I left off in that last presentation, and it just reminded me how much work we've accomplished. I've got only 20 minutes and we're already running late, so I'll try to make this quick. This is just intending to be a update on our recent efforts and current plans. I'll give you a real terse overview of what the mission is for people who are unfamiliar, and then move into some of the recent accomplishments and where we sit right now. I'll first point out that Resource Prospector actually has a spot, if you will, both in this slide, but also in the grander plan of moving from being Earth-reliant to Earth-independent. And what it is it's an ISRU demonstrator mission, an in situ resource utilization on the moon demonstrator mission. And a number of the talks that have already taken place, and even some of the awardees, have touched on some of the relevance that Resource Prospector could bring, namely to understand at levels better than current understanding on the polar regions of the moon about the horizontal and vertical distribution of volatiles, and then even possibly what could arguably be a separate mission, doing an early demonstration of how you might get at them and harvest them. So pretty important mission, very relevant for a number of discussions going on right now. For the people in the booth, there is sound. There we go. So this is an overview of the mission in classic NASA form, big dramatic video. This is a Falcon 9 launch. That's our design basis. We're looking at some other opportunities as well. I fast forward through to the point where we've separated off the launch vehicle. We're now TLI heading in. Present design carries a solid rocket motor to be captured by the moon. Fires off, and then once complete, we get rid of it. Happen in a moment now. You can see a rover-based system sitting on top of a very simple lander. We're a Class D, low-cost, kind of different type of mission inspired by what we accomplished with L-Cross. And so it's all about simplicity and cost-effectiveness, and we're risk-tolerant in order to enable that to happen. So we reorient ourselves for the ultimate descent. I guess we've been descending all along, but controlled descent now. And slow down with our braking thrusters here into an area that we pre-selected to have a very interesting mix of proximity to areas of interest, but also navigability, lighting conditions. We're a solar-powered mission. So this and a number of other constraints create quite a mess of a Venn diagram to try and find the perfect spot with timing and everything else. Now representing the rover coming off, this is a neutron spectrometer system hanging off the front. You'll see why that's there in just a moment. Get on sun immediately. The existing design of the Resource Prospector mobility system can crab walk, so it can stay on sun as much as possible while it's going off and doing initially some surveys. This is doing the X, Y, Z distribution measurements represented very simply here. Looking down into the regolith, say a meter deep with the neutron spectrometer system, and just doing a XY mapping and also a vertical mapping, but without actually touching the volatiles yet. When we get to an area of interest, showing right now is coming up into one of those permanently shadowed regions on the north or the south pole, depending on which pole we go to. We then go on in and find an area of special volatile interest, and we start drilling. So there's a drill system right here that you see being lowered. There's the neutron spectrometer again. Then underneath the rover, in this simple representation, is a near-infrared spectrometer. So it's taking a look at what's being pulled up and the tailings being dropped onto the surface of the moon, and we're also bringing materials up being collected into crucibles inside the body of the rover. It's been very cold in there, maybe 60 or 70 degrees Kelvin, so we get out before we do processing, get back on SEM, get power positive, and then use an oven system to volatilize what's in the soil. So we cook it, and then over here you see a stop-action video done in the lab, trying to represent what you might be able to see with the effluent coming in and condensing out, and you drink the soil that you found up there on the moon. You go back and do your prospecting over the remainder of the life of your mission. We're not designed to make it through the lunar night, so depending on your location, it could be as short as a 6 or 7 day mission. It could be a dozen days or more, and then if you really work hard at it, you might be able to get very clever walking around rims of craters and so forth and extend it considerably longer. So back in fiscal 15, which was October 1st in 15, we started on a really clever idea. And that was to try and go through an entire mission life cycle in a year. Not to actually go to the moon, of course, but start with requirements in October. Go through all the design gate reviews. We actually simulated the gate reviews in order to train the team into the types of things you might see. I actually used the requirements, even though we didn't have a formal review board. Designed the system, built the system, and actually flew the mission remotely, terrestrially, all in a year. And that's what I'm going to walk you through. Last year, for those who are here, we just started touching on this topic. So you see some video here on the right side. This is some payload system representations. You can see a drill here. See the oven system represented here, and in the bottom right corner, that's 2 times sped up activity for crucible handling. This is the crucible here, and it just got dumped. It's moving around, it's getting weighed, caps are coming on and off. And so this is a software development platform. Up top, you see actual material going into a 3D printed crucible coming off of this part of the drill. And we're just studying how effective this is. You can see we're losing a lot of material off to the side. So this is a great prototyping means to see how effective we are if we need to have some chutes, if it needs to be redesigned. We're in phase A right now, so this is pretty good, relevant work to influence what will ultimately become our preliminary design. And by the way, you could follow the dates up in the top left corner as we're going forward here, how things are progressing. So we zoomed past all the design review stuff to get to the attractive, fun things here. But now we're in June of last year. You can start to see the mobility system being built, gorgeous stuff. This is being done at Johnson. This is one of the suspension systems and wheel systems. We built 5, one to be used as a test tool, and then the other 4, of course, to go on the rover. Rover's starting to come together. It's nominally 1.5 meters by 1.5 meters, and if you go to the top of the mast, around 2 meters tall. And then this takes a little while to load. Oh, it's the next one. So this is the RP15 Rover, as we came to call it, because it was taking place in fiscal 15. You can see all the key elements in here. Many of them are intended to be ETU versions of flight. Some of them are utter fakery. For example, this isn't actually a functioning solar array. We didn't need to worry about that. We actually charged the system on an umbilical, removed the umbilical, and went out and used it. But we did have flight-inspired batteries down below. This is an actual honeybee drill system that is an ETU version of what we'd like to fly. There's vision systems up above. Near-infrared spectrometer down below that you heard me illustrate in the video. A neutron spectrometer hanging off the front. You could read the rest. And then we actually built it and started testing it. So now we're out in August of last year, and we were running it around at the Johnson Rock Yard. We also have a Roverscape equivalent here at Ames. Later this fall, we're intending on bringing it here and doing some more software testing. Ames is doing the software and nav work for the rover. You can see it's fully full degrees of freedom, three different degrees of freedom capable for the mobility, which makes it very good at handling different obstacles that may come in the way and so forth. But this is really a test bed to test the software, to test things like how you might make it over a rock, how you do things like redistribute the load across the rover. You'll see in a video coming up, we could actually move the load around, which could help us get out of difficult situations. See here, we're not moving the load around, we're really leaning into it. Some more stills of the actual drilling taking place. This is the RP15 Rover. You could see, in this case, it's largely just play sand that's out in the rock yard. But you can see the materials getting caught in the flutes of the drill as they're supposed to, and then they get wiped clean by this metal brush, and that's what drops out and then fills this crucible, which is pushed outside the body of the rover to be filled and then brought in and does all the stuff that you've seen already in video. It was Houston, so we had to navigate some of this stuff. This came on in an hour. It was a sunny, beautiful day, and then it was this. Ryan Vaughn took this picture out his rental car front window. He did get in there and help. He didn't just stay in there where it's warm. This tent that you see here is where the guys are. You see it's being pushed over by the wind. Water started coming in underneath it. Guys quickly made a moat around the rover, successfully kept it dry. Heroes, all of them. And then it passed just as quickly as it came and loaded the rover up and brought it back, and it was, of course, fine because of the heroism of the team. Now, ultimately, now we're out at the end of August. This was the big culmination for this RP15 activity in fiscal 15. This is where we actually flew the mission. We had the rover sitting out in the heat at Johnson. We had the main operations office here at Ames Research Center. We had the payload team operating out of Firing Room 4 at Kennedy. And great story with this picture right here. You notice the kind of interesting frame around it. When we got out into the yard, the vision system had a total whiteout condition. Turns out the calibration of the cameras wasn't appropriate for that Johnson bright light, and so it was total whiteout. Everything looked like the top part of this here. So one of the engineers who was out there in the field immediately took one for the team. He took his sunglasses, snapped them in half along the nose bridge, and then duct taped them up over each camera, the left and right side. So this is the right camera, I believe. And magically we could see what we were doing, and on we went. We recognize that won't be a viable means when we're on the moon. See Tony Colaprete and Rick Elphick here looking at the data coming off of Nervous. Got the red-blue 3D glasses here because you could actually illuminate the area underneath the rover with different frequencies, different LEDs that you activate, and so you could actually get different appreciations of the data you're looking at by looking at it in different ways, different filters. Some very clever tools are being developed along with this too, so I'm showing you a lot of hardware, but it's much more than that. This is actually what's called the Verve tool, and it's our rover driving tool. It's incredibly intuitive. I didn't get the opportunity to actually do it. Don't know anyone would allow me to, but you can see here we actually have a representation of the rock yard there, a representation of the rover, fully functional, all the degrees of freedom in the animation. And so you could do things like take your actual joystick and move it around in position as the driver, and then set up your waypoints. That's represented by some of these kind of pylon-looking things here. And the rover would go ahead and move in that fashion. Very intuitive, as opposed to some sort of command line entry or so forth. Now we're moving into fiscal 16, and this is in the Argos facility. It's a gravity offload facility. You could see the structure there. It's now operating in 16G. It's in an office environment, actually in a laboratory environment, so it's obviously not in the right thermal and pressure conditions. But it allowed us to see trade on a relative basis, relative traction capabilities, and look at grouser designs and so forth at different angles in a lunar gravity context. And so this was very useful. It always results in some sort of surprises, some things you didn't expect. We also played with the idea here. You can see we're back to our chevron design wheels, and this is what we're using out in the field, of coming off of a lander. This was one lander design that had some pretty steep ramps. You know, it's different than what you saw in the video. And this was one of the partners that we were potentially talking to about providing a lander, so we had to check out the capabilities there. We're still in the gravity offload facility. That's why the video looks very counterintuitive. That looks like that should just come sliding down. It's not being held back by the strapping there. It's really performing as it would in 1/6 the normal force on Earth. And here's some studies back in the bed. I think this is at 0 degrees slope. And look what happens right here, floating in air. And that's a really good illustration, even though that isn't necessarily what you would design to. It shows you how you can completely redistribute the load across this rover design. The other 3 wheels took the load as it was going up and over the rock, and then it actually allowed that end to float. And going in and out of potentially risky areas, unknown areas, super soft, permanent shadowed areas, maybe that'll be a value. And this is something we're considering, the relative value of that versus the complexity, which ultimately is your enemy on cost and potential risk. And then now, again, still following the dates, this is a couple months ago, in the thermal vacuum chamber with some of the rover systems, you can see one of the suspension systems actually undergoing tests in a TVAC chamber and operating it at those conditions, so it's a vacuum, it's cold, and just seeing what happens at these cold conditions. Of course, not 70 degrees Kelvin, but very cold. And we're just learning from it again, being in phase A. This is a vibe test. You can see if you look carefully, it's actually moving. You can see some structure going through bending modes, shaking up here and so forth. We've taken a number of systems, including the drill and the oven system, various, all 3 degrees, XYZ vibe, and actually trying to understand again the design. This is not intended to be flight hardware. So parts of that we don't care about the response, but other parts of it we very much do. And we found things like the oven arm, the actual axis of rotation in there had some bearing issues, and so got to investigate that and understand why that was, all in advance of preliminary design, which is pretty impressive to be able to get to this level of maturity this early. We've been talking lander partnerships. I don't recall last year if I probably brought this up, but there's been a number of different international partners that we've been talking about for providing the lander. This is actually strongly encouraged by the US government, okay? And so we've met with a number of different parties right now. We're having an excellent engagement with Taiwan. And so you can see in the top picture on the right, that's a partial build of our lunar lander concept that you saw in the video, done by Taiwan. And that's all of our team went during a visit to Taipei. We've met a total of 5 times so far, and the discussions are going quite well. The bottom picture there is us during one of our meetings again in Taiwan. So discussions are going well. We had an initial 6-month study period to just see if this was a fit. Frankly, we needed to be convinced if they were capable of doing this. This is a stretch compared to what they've done in the past. And we've just now started a 1-year extension, not quite through the signatures yet, to be able to then use that period to start developing the flight agreement. And so a lot of agreements have to happen on both sides. This is not a done deal for the mission yet, but that's where we sit right now as far as our partnership goes. So my closing slide here, about the mission, all about the volatiles and their distribution and the demonstration. The RP specs, just in sort of a snapshot form. Mission life, nominally that amount of time. It could be much longer, but it's really about successfully accomplishing the demonstration that we wish to do, and strictly speaking, nothing more. That's what cost-constrained mission, that's how they think. And so if we were designed for just a few days and then ran for 10 months, there's a certain argument that says that was a fail because you're consuming money all the way through that. Get what you want done and then get out. And so you can see the relative size here. I have another slide that I'm not going to show, but it shows the relative comparison of this. This is very similar in size, all the shapes different to, say, Spirit and Opportunity. And footprint, maybe not too far from the Lunar Cod. And then finally, here's where we sit in our project timeline. So you heard me describe RP15. Fiscal 15 was that impressive demonstration, and then 16, which we're about halfway through right now, a little more, is all about the environmental tests. So we're learning from our design, first by applying it field, now by beating it up and seeing how we can improve the design. The intention is that next fiscal year, near the end of it, after we get all of our agreements in place and so forth, we start the gauntlet of gate reviews, starting with the system requirements review. And I think that's everything I have. So thank you.
So we could take perhaps one question if someone has a burning question for Dan. No? All right. Thanks very much. Yeah. So we fully